knows it rains a lot here. If I can collect all this down one downspout and make hydroelectric power.
Rain is everywhere, yet we treat it like a nuisance and shove it into gutters. Imagine if your roof could turn a storm into clean electricity. A research team in Singapore says that it is now possible. They built a simple device that turns falling raindrops into measurable power, and they report outputs up to 100,000 times higher than older raindrop power ideas. The secret is not a rare metal or a spinning turbine. It is a clever flow pattern that makes charges separate again and again. Let's unpack the trick, the physics, the numbers, and the tough questions. Hydropower's success and the ceiling. I'm Dr. Jakob, and in Germany we say Los geht's. Before we talk about raindrops, we should respect the giant of water energy. Hydropower is one of humanity's oldest green tools. We used water wheels long before we had modern power grids. Even today, it supports many countries with stable, low-carbon electricity. In Germany alone, more than 7,300 hydro plants feed into the network and deliver around 20 terawatt-hours each year. That is a solid slice of renewable electricity, built on a technology that can run day and night. Worldwide, hydropower produces roughly 4,250 terawatt-hours annually, making it the largest single renewable source of electricity. But the easy sites are already taken. Many rivers are already used or protected. New megaprojects face environmental limits, social resistance, and long approval times. In many places, the era of building new huge dams is slowing down. The remaining potential exists, but it is harder, slower, and often more controversial. So if we want more power from water, we must look beyond rivers and reservoirs. That is where rain becomes interesting. It falls on rooftops that are already sealed. It is collected anyway, then wasted in a gutter. And unlike rivers, every city has rooftops today, in every neighborhood, ready for small, local experiments. The hidden physics at the wall. The key idea is charge separation at an interface. On a tiny scale, a small fraction of H2O becomes ions. When water touches a solid surface, those ions do not behave the same way. The surface favors one sign, so an electrical double layer forms at the boundary. Now add motion. If water flows through a tube, part of that charged layer is dragged along with the flow, while other charges stay near the wall. This creates a voltage between the top and bottom of the tube. Connect the electrodes, and a current can flow. Researchers tried to boost this by shrinking channels. Nanotubes and microtubes offer lots of surface area for little water. But nature set two traps. First, capillary forces. In very thin tubes, water clings to the walls and may barely flow. To push it through, you need pumps, and pumps often consume more energy than you harvest. Second, the Debye length. It is the distance over which separated charges survive before they screen each other out in the liquid. In very pure water, it can be a few hundred nanometers. Beyond that, charges cancel quickly. So only a thin layer near the wall truly contributes, and continuous flow wipes out most of the benefit. One more subtle point matters here. With continuous flow, the liquid also carries mixed ions that quickly screen any separated charge. That screening is why many older designs looked great on paper, but disappointed in real measurements. Why rain is an untapped battery. Think about what rain does in a year. In a wet country like Germany, annual rainfall can add up to close to a meter. On a normal roof, that means huge volumes of water arriving for free, carrying potential energy simply because it starts up high and ends up down low. Most of it just drains away. We designed gutters to remove it, not to use it. Solar panels help, but sunlight comes and goes. Clouds cut output. Night cuts it to zero. Rain arrives at exactly the moments when solar is weak, so the two sources can complement each other in a very natural rhythm. If your roof could harvest both light and water, you would have a more balanced system across seasons and weather. For years, people tried to harvest electricity from raindrops. Many experiments worked, but only at tiny power levels. They could power a sensor or charge a capacitor slowly. It was proof of concept, not infrastructure. Then a team from Singapore published results that made many engineers look twice. They report outputs up to 100,000 times higher than earlier raindrop approaches, by avoiding a limit that used to choke the current. They did it with simple parts and gravity, not with exotic materials. If that holds outside the lab, it changes the conversation. So how do you get electricity from water without a turbine? You use the fact that water and a solid surface can trade charge whenever they touch and move. The Singapore trick: making water into pearls. The Singapore team changed the question. Instead of forcing water into a smooth stream, they broke the flow on purpose. A small reservoir sits above the device, like a pipe or gutter. At the outlet is a thin metal needle. Water drips through it and hits the inside of a vertical plastic tube made from FEP. The tube is not microscopic. It is about 2 millimeters wide inside and about 30 to 32 centimeters long. Because of the drip entry, the water forms a chain of short water plugs separated by air. Water, air, water, air, like a string of pearls. This is plug flow, also called slug flow. At the bottom, the water lands in a metal cup. The top needle and bottom cup are wired into a circuit, so voltage and current can be measured. Every passing plug creates a fresh, moving boundary. The wall gets wet, then dries again behind the plug. That retreating edge is where charge separation becomes strong. Hydroxide ions tend to stick to the wall, leaving the moving plug more positive, and that positive charge travels onward. Because this repeats many times, charges stay separated over centimeters, not nanometers. That is how the design sidesteps the Debye limit. Numbers that sound small until you scale them. Physics is nice, but watts decide the future. In the lab, the team reports an energy conversion efficiency above 10%. That means more than 1/10 of the water's gravitational potential energy becomes electrical energy under their test conditions. In one setup, a flow of about 80 milliliters per minute ran through a 32 centimeter FEP tube with a 2 millimeter inner diameter. The average output was about 440 microwatts from a single tube. That will not run a kettle, but it is steady, and it needs no turbine. With enough tubes, you could imagine powering small rooftop sensors, weather stations, or emergency lighting that only needs a trickle. The authors suggest the approach could reach up to about 100 watts per square meter, with dense packing and ideal flow. Modern photovoltaic panels in strong sun can exceed 200 watts per square meter, so rain power is not a replacement. It is a companion. When it rains, solar output drops but does not vanish. Many panels still produce perhaps 10 to 15% of their rated power. Depending on the storm, that could be tens of watts per square meter. Add a rain harvester and you smooth the dips. The team also argues that the system can tolerate common contaminants like small amounts of salt and can handle temperature changes. Most importantly, it works by gravity alone. No pump is required, so the energy balance stays honest. The big but. Real roofs are not clean labs. Now for the big but. A lab tube is polite. A rooftop is chaos. First, the device depends on keeping the flow discontinuous. Strong charging happens mainly at each water-air transition, at the retreating edge of each plug. If plugs merge into a continuous stream, output can drop sharply. So the geometry must maintain plug flow in drizzle and in downpours. Second, scaling is modular. Tubes longer than about 32 centimeters did not add performance in their tests, so you need many parallel tubes for more power. That adds wiring and installation effort. Third, maintenance. Real rainwater carries dust, pollen, soot, and tiny leaves. Narrow tubes can clog, and algae can grow. You would need filters, self-cleaning designs, or easy swap-out parts. Fourth, durability. Frost could split tubes. Hail could crack housing. UV light can weaken polymers over the years. Fifth, cost. A small-scale FEP hose can cost around €5 per meter. One rough estimate suggests thousands of meters of tubing to cover about 10 square meters densely, pushing material costs into the tens of thousands of euros before labor. Solar is cheaper today, often by a lot. A small rooftop solar install might be a few thousand euros for several square meters, depending on the country and incentives. Rain systems would need a similar cost curve to compete, and that is a hard hill to climb, though costs might fall with mass production. Finally, there is competition. Triboelectric nanogenerators can harvest energy from raindrops using special surface layers, even on solar modules, with lab reports around 50 to 100 watts per square meter. So the likely path is hybrid roofs, solar for sun, smart rain harvesters for storms, and steady power in bad weather. So can rain really power our homes? Not by itself, at least not yet. But this plug flow approach shows something important. We have been ignoring small, everyday water drops. With the right design, even a gutter can become a generator. The lab results are promising, and the physics is elegant. Still, real rooftops bring dirt, cold nights, UV light, and years of wear. Costs must fall, and maintenance must stay simple. If researchers can solve those pieces, rain power could pair with solar and fill the gaps when skies turn grey. Keep watching closely, because storms may pay us back.